The Future of Food Waste, A Green Chemistry Perspective, an essay by Katie Privet, presented by Ben Newbern. Based on a study by the United Nations Food and Agriculture Organization, 1.3 billion tons of food waste is generated every year. This amount makes up 1/3 of the food we grow annually. This waste must be minimized. It can be accomplished by properly educating consumers about post-consumer waste while improving the storage, processing, and disposal of food. However, there is some food waste that cannot be avoided, like straw from farms, orange peels, seafood shells, and spent grains, to name a few, which were never directly intended for human consumption. These unavoidable food supply chain wastes, or FSCW, often end up in landfills, where they affect soil quality, pollute water sources, and release methane as they decompose. As disposal costs rise and social acceptability of landfills diminishes, new methods for the processing of waste must be employed. According to the 7th principle of green chemistry, which states that resources should be renewable when technically and economically feasible, FSCW show great potential in acting as a cheap foodstock for chemical processes. And according to principles 3 and 6, these chemical processes can be conducted in a low energy and minimally hazardous manner. This is a more economically practicable disposal and reuse method as compared to having to pay landfill taxes and fees when FSCW are disposed of as waste. A simple way to gain value from FSCW would be to convert it into fuel. FSCW can be turned into fuel and fertilizer through anaerobic digestion, which allows the mixed biomass waste to be converted through microbial processes. Although it would be very difficult to establish a high-efficiency process that can match the prices of the long-established fossil fuel industry, FSCW-derived fuel and fertilizer would help provide alternatives to their fossil fuel-derived counterparts, helping convey that a shift away from fossil fuels could be attainable. In an effort to remedy the efficiency disparity between products of the fossil fuel industry and products from FSCW, waste must be collected and processed at larger scales, where these concentrated wastes contain more easily accessible, high-value chemical compounds that have greater industrial use. Examples include agricultural waste at large farms, spent grains at breweries, and citrus peels at juicing plants. Agricultural waste can be utilized to make bio-based materials instead of simply being disposed of. Waste straw can be used to replace wood products in the wood chip boards used in furniture. The boards can be bound together using a waste biomass ash, as opposed to toxic silicate binders. These waste-based furniture boards are carbon neutral and non-toxic. For spent grain, after brewing has taken place, there are many potential applications. These include composting, where spent grains, a green matter compostable waste, can be used in a 2-to-1 compost ratio with brown matter compostable waste like leaves and straw. They can be used in bread and other baked goods to add flavor and texture. They can be used as a stock feed food supplement for cows, sheep, and pigs. In flock feed, spent grain can be used as a selenium nutrition source, which promotes efficient poultry breeding and better egg and meat quality. They can be used as a substrate for growing edible mushrooms, and they can be used for the creation of homemade dog treats. And finally, the orange juice industry could benefit greatly from properly utilizing its food supply chain waste. When oranges are juiced, over half the orange is wasted in the form of peels and piths, resulting in 22 million tons of waste out of 45 million tons of oranges that are juiced every year. Orange peels contain many useful chemicals, but the usual disposal method for the peels is to bury them deep underground, and there is virtually no benefit to be had when they're sitting under multiple feet of soil. The chemical compounds in the orange peels, like limonene, bioethanol, and pectin, can be processed and used for things like cleaning products, fuel, and jam. Limonene, a fragrant molecule, is used in detergents and personal care products. Bioethanol is used as motor fuel or as an additive in gasoline. And pectin, which is in both orange and apple peels, is used in many industries and has many potential applications. Pectin is used in the pharmaceutical industry for the preparation of suspensions, emulsions, cosmetics, and capsules. In the food industry, it is used as a film in packaging, a thickener, and a gelling agent in the manufacture of jams and preserves. It is used in wines as a dehydrator for plant tissues, and it is used in milk to precipitate casein. Why do we let these chemicals break down into a hydrocarbon mixture underground and then attempt to synthetically reproduce them when they can be directly taken from the peel using a mild selective extraction technique? The pectin extraction and purification process can be used to obtain high methoxyl and low methoxyl pectin, which both have industrial applications in the food and pharmaceutical industries, as previously stated. The traditional process for pectin extraction is explained here, but based on a study conducted by the Department of Food Science and Biotechnology in Korea, it can be improved with the utilization of non-hazardous acids. Less hazardous synthesis can be employed with the use of organic acids at a lower temperature instead of mineral acids at a higher temperature. Acids like tartaric, malic, and citric acid can be used instead of fairly hazardous acids like ammonia. With mineral acids, reactions occur at a temperature of 90 degrees Celsius, while they occur at 85 degrees Celsius with organic acids. This temperature should still be decreased, but it is comparatively lower than mineral acid reactions. The use of organic acids in pectin extraction has shown yields with higher molecular weight and viscosity, which demonstrates the possibilities of high efficiency using green chemistry processes. By utilizing FSCW as a feedstock for chemical processes, organic acids and compounds during chemical synthesis, and relatively lower temperatures during reactions, we can avoid using fossil-based resources, minimize chemical processing, and reduce pollution. This is my work as consulted, and thank you.